We have a few more derivative rules to generalize in this video. First up, we're going to talk about the general power rule, and I know what you're probably thinking. You're going to say, well, Mr. H, we talked about the power rule twice already. Why do we need to talk about it again? And, well, you would be right. The first time we talked about the power rule, we said you can take the derivative of y equals x to the p, where this power right here, p, was a positive whole number. So 2, 3, 4, 5, and so on. But if it wasn't of that form, then we couldn't take the derivative of it. The second time that we talked about the power rule, we said, okay, now you can take the derivative so long as the power is a rational number. So it can be negative now, that's fine. It can be a terminating decimal, it can be a fraction, but it only works for rational numbers. Here, this works for any real number p. So this is really nice in that this will work for any real number as long as you have x to a constant. And it works the same way that the power rule has always worked. It says if y equals x to the p, then y prime is p times x to the p minus 1. So I multiply by my power and subtract 1 from my power. So again, hopefully this is not a big surprise. We're just extending the power rule as far as it can possibly go here. You can also generalize this power rule to work with the chain rule as well. If you have y equals u of x, or simply u to the p power, you may have noticed this kind of general structure to derivatives that look like this. But we can actually give a formula here for functions raised to a power. So, okay, what do we do with these? We take the derivative of this outside part. Well, what would that look like? I multiply by my power. Inside part stays the same. Subtract 1 from my power. So there's the derivative of the inside part. And then the chain rule also says we multiply by the derivative of that inside part. But we multiply by u prime. You may have noticed this in the chain rule as you were going through problems that look similar to this. If you didn't, like I said, it's no problem. You don't have to memorize this formula. It can be a nice way to speed up the process of taking derivatives, but you are certainly not required to use it. It just can be helpful to use from time to time. So I'll show both ways again. I'll show finding the derivative using this kind of shortcut and then using the chain rule. So let's look at some examples here with our general power rule. First up, I have y equals x to the e. You say, well, geez, Mr. Huber, that's an easy one. That's not even a power rule. That's y prime equals x to the e. And I'll say, hold on a minute there. Hold on, not quite. You've got x to the e confused with e to the x. These are two different functions, and we need to keep those in mind. This is a really, really easy trick question to mix up here. So here I have y equals x to the e. Remember, e is just a number. Remember, e is approximately 2.718, blah, blah, blah. It's an infinitely long decimal. It's an irrational number in the same way that, say, pi is. But e is still a constant. So I have x raised to a constant power, x raised to a power. I have x raised to a power. This is actually just a power rule. So what does the power rule say? Well, it says when I take the derivative, I'm going to multiply by my power. So I'm going to multiply by e times x and then subtract 1 from my power. E times x raised to the e minus 1 power. And yeah, I could maybe give a decimal approximation, but this is more exact. This is the better way to write your answer. So y prime is e times x to the e minus 1. And then I said, hey, please, please, please try not to mix up x to the e with e to the x, because that derivative is much, much different. Derivative of e to the x, we've seen that before, is simply just e to the x. So please keep an eye out on quizzes, on exams. This is a trick question that I like to throw in from time to time. It's a really easy one to mix up if you're not paying attention. C I have y equals 2x cubed plus 5x minus 4 raised to the pi power here. And I'm going to do this two ways. First way I'm going to do this is I have to use the general power rule no matter what, but I'll show this using the structure that we've been doing the chain rule problems with, and then I'll show that we actually get the same derivative if we use this shortcut. So if I'm looking at this, I see this function 2x cubed plus 5x minus 4 raised to the power of pi. And remember that pi, at the end of the day, it's just a constant. It's a fancy constant. It's an important one. It's 3.14159 and I think 826 after that, but I don't know. This is a function raised to a power, so this is a chain rule. So u I would take to be the inside function, which in this case is 2x cubed plus 5x minus 4. U prime would be 6x squared minus 5. So when I take the derivative of this function, I want to first of all rewrite it, y equals u to the pi power. And then when I take the derivative, u to the pi, okay, this is a power rule. So I'm going to multiply by my power. So pi times u, and then subtract 1 from my power to the pi minus 1 power. So I can rewrite this if I plug in u and u prime into this expression. I'll have pi times 2x cubed. Oops, what did I forget? I almost forgot my chain rule. Remember, the whole point of this was me using the chain rule, and I almost made a mistake. I have the derivative of this inside part, but what am I forgetting? I'm forgetting my u prime. So don't do what I just did. Don't forget your u prime. Remember, at the end of this problem, I need to multiply by u prime. So now, okay, now we'll go ahead and take the, we'll plug in our u and our u prime, rewrite this function, or this derivative, so that it's in terms of x. So I have pi times u, that's 2x cubed plus 5x minus 4 raised to the pi minus 1 power times u prime, well, that's 6x squared minus 5. I would probably just leave my answer like that. You're really not going to simplify much beyond that. I think that's a good place to stop your answer. And you can probably actually see pretty easily here that I'm going to get the same thing if I just use this formula. And so let me show using that formula that I'll get the same thing. So if I have y equals 2x cubed plus 5x minus 4 to the pi power, so here is my u of x, that's my u, y prime, that's this part right here. What does it say? I multiply by the power, so I'll have pi. Inside part stays the same, so 2x cubed plus 5x minus 4. Subtract 1 from my power, so pi minus 1, times the derivative of that inside part, times the derivative of u prime, so multiply by the derivative of the inside part, so I should have 6x squared plus 5. We see we get, hey, this is the exact same derivative that we got using the chain rule. So it doesn't matter which way you go about it. If you're feeling, most comfortable using the chain rule, then continue to use the chain rule. But this shortcut can be nice. It can save you a little bit of time. You are not required to use it, though. A couple more that we'll look at here. These we saw, I believe, back in, what section would that have been in? Probably 3.7, if I had to guess. Or no, we learned this with the quotient rule. That would have been 3.4. This I could use the quotient rule on. I could just use the quotient rule, but I can also rewrite this expression as x to the minus 2 power and then use my general power rule on this. So y prime says, okay, when I take the derivative of x raised to some power, I'm going to multiply by my power, negative 2 times x, and then subtract 1 from my power. Be very careful, though, with your negative. Remember, we're subtracting 1, so we'll actually have a minus 3 power now. And I can leave it like that, or I could rewrite this as negative 2 over x cubed. If you preferred a positive exponent like I do, I think either one of those is fine. Lastly, root functions. I believe we looked at these earlier as well, but just in case we didn't, or in case we need a little bit more practice here, I look at this part right here. I'm going to rewrite that expression. The cubed root of x to the 4th really says x raised to the 4/3 power. So I have x raised to a constant power. This is a power rule. So I'm going to take the derivative y prime. The power rule says I multiply by this power. So I'll multiply by 4/3. This part stays the same. I'll multiply by x and then subtract 1 from my power. Subtracting 1 from my power would give me 1 over 3. You could leave your answer like that. If you really wanted to, you could rewrite this as a radical, 4/3 times the cubed root of x. Most of the time, though, I'm just going to leave it as a rational exponent. I think that's just easier to work with. But if you really like using radicals, then of course you can write it using radicals as well. Last thing that I want to talk about in this video is the derivative of logarithmic functions. And earlier we talked about the derivative of y equals the natural log of x, but just like when we were talking earlier about derivatives of exponential functions, we knew the derivative of, say, y equals e to the x. But we said, well, what if this base of this exponential isn't e? What if it's y equals b to the x? And we saw that it was similar, but it actually did look a little bit different. Now, when we're working with y equals natural log of x, we actually do have a logarithm here. This is y equals log base e of x, right? These two expressions say exactly the same thing. We just never really write y equals log base e of x. We always write y equals natural log of x. But I want to actually ask myself the same question. I'll say, well, what if the base of that logarithm is not e? What if we have, say, y equals log base b of x? What happens if I'm working with the common log base 10, or log base 4, or log base 20? What do those derivatives look like? And it turns out it's going to look similar to y equals natural log of x. We're just going to have a little bit extra added in there. So first up, it says if y equals log base b of x, so this is the general logarithm that we'll be working with. Think about the derivative of y equals natural log of x. That was 1 over x, and hopefully you'll see that right here, 1 over x. We'll see that 1 over x kind of coming through. We just need to multiply that as well by the natural log of whatever our base is. So in the denominator, we'll be multiplying by that natural log of b. This part right here for x greater than 0, again, this is simply just stating the domain of the logarithm function. I know that logarithm is only the domain of it is only positive numbers. It doesn't work with negative numbers. It doesn't work with 0. So we just need to be aware of that. Not going to have a huge impact on our derivative, and you certainly don't need to mention this when you give a derivative. And just like we said before, when you have absolute values inside of a logarithmic expression, it's not going to dramatically impact your derivative. We'll see, hey, we actually get back the same exact derivative. The only thing that really changes is our domain, because when we're working with log base b of absolute value of x, then the domain is all x except for 0. So let's look at a couple of these. First, I have y equals log of tangent of x, and this one's a little funny because there actually is no base written. When there is no base written, this is actually called the common log. It assumes that we're talking about log base 10 of tangent of x. So we have log base 10 of tangent of x. This then, hopefully we can see, hey, tangent of x. Well, that's inside of our logarithm function. This is a chain rule problem. So off to the side over here, I'm going to say, well, u, that should be tangent of x. U prime, derivative of tangent, that's secant squared x. So I really have y equals log base 10 of u after I make that substitution. So let's take the derivative and apply our chain rule. Y prime, the derivative of log base 10 of u. Here I'm going to be leaning on this derivative for the derivative of the common log. So this will be 1 over x. Again, this part hopefully reminding you of the derivative of y equals natural log of x. The only difference, the only major difference is that in that denominator, we have a factor of natural logarithm of our base. Our base this time was 10. So times natural log of 10 times u prime for our chain rule. And actually, I noticed one small mistake here. Notice right here I wrote x. I should have written u because this is a function of u instead of x. So let me just go ahead and fix that real quick. So I should have had u here. And then the last thing I'm going to do, I'm going to take my u and my u prime, plug those back into my derivative function. So this is really 1 divided by u, so this is tangent of x, times natural log of 10, times u prime. Well, what is u prime? U prime is secant squared x. Here is my derivative. If you'd like, you could leave it like that, or you could also move that secant squared x up to the numerator as well. I don't think it particularly matters whether you put it off to the side over here as a, well, don't write it as another fraction, but if you write it over here as a factor, or if you put it as your numerator, I have no strong preference as to how you write your answer. One last problem that we'll look at in this video. Here I have f of x equals log base 2 of log base 2 of x. This one is kind of weird. We have log base 2 appearing twice. It's not a typo. So the first thing I want you to look at is I have this log base 2 of x inside of this log base 2 function. This is yet another chain rule. A pretty common occurrence here. So for our chain rule, I need to identify my inside function, and that will be log base 2 of x. So I'll choose u to be log base 2 of x. U prime, what does the derivative of this guy look like? Well, that's going to be 1 over x. It's similar, remember, it's similar to natural log in that we see that 1 over x. But in the denominator, we just have that factor of natural log of our base. Our base in this problem is 2. So I have 1 over x times natural log of 2. So this is not the derivative of f of x. This is simply the derivative of log base 2 of x. So let's go back here. Let's rewrite this expression. F of x is equal to log base 2 of u. And this is something that we know how to take the derivative of. So let's go ahead and take this derivative and apply our chain rule. F prime of x is equal to, oops, not log base 2. It's going to be 1 over u times, well, natural log of whatever our base was. Well, what's our base? Our base in this problem is 2. So times natural log of 2. And then because we're using the chain rule, we need to remember to multiply by the derivative of that inside part. So the derivative of u, which we're just calling u prime for right now. And then, okay, now we can just simply take our u and our u prime, plug that back in for f prime of x. The most difficult part of this problem is done. So let's see, 1 over u is log base 2 of x times natural log of 2 times u prime. What is u prime? Well, that's 1 over x times natural log of 2. If you wanted to, again, I think leaving your answer like this is perfectly fine. If you really wanted to simplify it, we could simplify just a little bit. We could say, oh, how would I write that? I think I would write that as 1 over x times log base 2 of x times natural log of 2. I would just say natural log of 2 squared. No matter how you write this derivative, it's really not going to look pretty, so I think either one of these would be perfectly fine. We won't see derivatives of general logarithms all that often, I'll admit. Most of the time, we'll be dealing with y equals the natural log of x, or y equals e to the x. We're working with the natural base the vast majority of the time. But we will see these pop up every now and again, so we don't want to forget those derivative rules so that we have them for when we need them.